Thank you all for joining me today for this presentation called Sequencing the Student Genome, which is about modeling click-level behaviors in Snowflake ML. My name is Allie Ferris. I am a data scientist at Anthology. I've been with Anthology for about 6 years. I've been on the data science team since 2022. Previously, I was in some more client-facing roles, helping them with data integration into our products and analytics consulting, helping them with some of our data analytics products. So I really try to bring that client-facing perspective to all the work that the data science team does. In a previous life, I was a librarian. Education, supporting education has always been really important to me. So that's part of, how I ended up at Anthology. And we are a SaaS company in the higher education technology space. So we have a whole ecosystem of products across sort of the university life cycle, whether that's going to be admissions and recruiting, course learning management systems, student affairs, course evaluations, and all the way through to like alumni outreach, fundraising. And sitting over all of that, we have Illuminate, which is our holistic data reporting platform to unite the siloed sources of data from across campus. And so this brings in data from all of those products, which really increases the value of using our products across that ecosystem, right? You can have just one or you can have all of them. And being able to connect all that data together in Illuminate is a big selling point. So this is where Snowflake comes in. This is a platform that we use for Illuminate. We use that for bringing that data together into our canonical data models, surfacing descriptive and predictive analytics and reporting to clients. And for those clients that have the willingness and the capacity to get their hands dirty with the data themselves, they have Snowflake Reader accounts where they can do all of that work. And one of our products, which if you've been in college in, say, the last 25 years, one of our products is Blackboard. So you may have taken courses in Blackboard, especially if you were taking online courses, COVID times, et cetera. So that's actually the product that I'm going to be talking about a lot today, is data coming out of Blackboard. And Blackboard is one of Snowflake's older customers. So we've been on Snowflake for what was previously called Blackboard Data, now it's called Illuminate, for many years. So our data science team, our mandate is to work on data-informed products models for within the products, right? So we are taking data from across those products, building models, building features, pushing them back out into the Illuminate platform, where they can either be used for reporting purposes, for surfacing in dashboards, or pushed back into the point solution products themselves. The agenda for today, I'm going to talk a little bit about the project goal and the project itself, why we're using Snowflake ML for that, how we move forward with feature engineering in Snowpark, model training, particularly on container compute and some of the new ML jobs functionality that's being released, and talk about our next steps. So this presentation is going to talk about the project itself and the research that we're doing, because this is really an ongoing research project. But we are primarily also using this from a broader perspective to assess how we can transition more of our work onto Snowflake ML, see the value there, see the challenges, and how we can adopt that for our data science team's development and research processes. So we'll talk a little bit about the project itself, more about Snowflake ML and how we've been using it. So project goal is to derive behavioral patterns from site navigation data. So this is click level data in the site. If you were in Blackboard looking at your course, it's, I clicked into the course, I went over, to check my grades, I had to turn in this assignment. All of those clicks that you make are coming in through our telemetry data. And we want to take these sequences to create, what we're calling students' behavioral DNA, their profile, and uncover common patterns of ways that students interact with their courses. The ultimate goal here is really to give advisors and instructors a view into how students engage with their courses to better support them and understand their learner needs. Now, we've done work in the past that is already, deployed and being used in our advising products, which is looking at, say, student engagement in courses. And that's from a much more quantitative perspective. How many times did you log in? Did you log in as soon as the course opened up? If you're really eager to get into all of the resources, how many logins, things like that, different submission counts. And we wanted to really push that and expand to something more qualitative that could also give a descriptive view for those instructors, to know this student really they're not very deeply engaged when they do log in, because you could have two logins of the same length that are very different behaviors, right? Someone may be deeply engaging with the content. Someone else may have just left the tab open, right? So we wanted to be able to get at that. And so our approach for this is to encode that site navigation sequences. We're looking at it at the student course login level, because we tie all of our engagement scoring to the course itself, so we can look at success in a course. Did someone pass or fail? What kind of behaviors contribute to success in a course? And then we're going to take those and cluster them to identify interpretable personas, session types, different types of behaviors that we can see from this data. All right, so what is this telemetry data? You can see just a little example of, dev test data there. It's collecting user activity as they navigate through their course materials in our learning management system, Blackboard. So these sequences of page views within a given user and course login are then transformed. We take the page descriptions, the URLs, and all of the other, page identifiers, categorize them, and, calculate how long they spent on each page to create those processed sequence data. So every single click in every single Blackboard institution, it's a lot of clicks. This is 140 billion rows of telemetry data collected since May 2021, which accounts for about 8 terabytes of data, telemetry data in production. The data science team specifically, we work on a research data set for doing the research before things are put into production. And this is approximately 80 institutions that have given us, in their contract, permission to do research on their data for product improvement data science projects. So on that research data set, there's about 10 million new rows per day coming in that we have access to for our research. So, probably our biggest data set. This isn't something like some of the larger financial institutions and things that you will see, this week. But for higher ed, we are one of the bigger companies, and this is our most granular, biggest set of data. And for that reason, it had really gone underused before. There's some tables that aggregate from it, but at this granular level, we really hadn't used it before. And it's part of why we chose it for this project, because we wanted to see how the power of Snowflake ML could help us to unlock that data that we were really not getting anything to the extent that we thought we could. So that's why did we choose Snowflake ML. So to talk a little more about that, I'll talk about how some of our previous work has been, the research been conducted and how it's been deployed. And you'll see here, like I said, we've been a Snowflake customer for a long time. All this data is on Snowflake, but the data science team was really only using Snowflake to read, to query, to get the data that we needed. So for research, we're pulling out the raw data from queries, doing that feature engineering, that processing. We make heavy use of data version control, which is a open source package for data science pipelines. We find it very useful. So that's what's orchestrating all of those pipelines. The data is then stored in our S3 buckets. We're running those processing jobs, training jobs, anything like that on EC2 instances. And then ultimately, when we have a trained model, that's going into our internal artifactory, where it can then be used, installed in our AWS Lambdas that we're using at inference time. So reasons that we chose it, it's simple. Like I just said, our data's housed in Snowflake. We're pulling it across platforms twice to perform our feature engineering for training, for inference, ultimately going back into Snowflake. Another big thing is the reusability. Because all of our Illuminate analytics teams and other products are getting data from Snowflake, we wanted to be able to surface our work in Snowflake as well and be able to collaborate more effectively. So, we can say we've created, we may have created this model for this one product, for this one project, but maybe another product team, because like I said, we have a huge ecosystem of products, maybe they see use in it as well. For example, our other engagement score work is being used in multiple products right now. It's coming from Blackboard data, how people are engaged in their courses, and that's used for Blackboard, but it also goes over into our advising product so that the advisors have a dashboard where they can see, student engagement in their courses and prioritize and triage their workloads, because they have huge caseloads of students and they need to know who's going to drop off before their grades drop off, right? We know that disengaging in your course is, can predict future failure in the course. So we want to know when people are disengaged so that their advisors can reach out to them. So just some of the ways that that is pushed into other products as well. And the other thing is the scalability of the compute, just to fit the demands of a given task. Previously with our other, previous system, we, you need a bigger machine, you need to specify a bigger machine for that whole job, for that whole pipeline. Whereas using Snowflake ML, we were able to say, okay, I know, this scaling task isn't going to take too much compute, but now when I go to train the model, let me size up my warehouse and then size it right back down so I'm not spending money on things that I don't need to be spending money on. So this is our goal here with Snowflake ML. We want to have that raw data then go into the feature views, which, those are being processed once for training and for inference. Of course, only using our research institutions for the training, but all of the data will then be processed for inference and pushing into production. So process that once, and then we can use that data for training and evaluation, take that model into the registry, the same data from those feature views for a wider set of institutions can be used for inference and sending, publishing those predictions within Snowflake. So, this obviously reduces the amount of data coming across platforms, really simplifies things, and creates less room for error, right? If there's duplication of code, there's different places for deployment and training. There's always the possibility that, something doesn't match up right? So this really simplifies things. But of course, nothing can be totally simple, because we have a development and production instances of Snowflake, and our engineering and architecture team has a pretty robust infrastructure as code, approach to Snowflake. So while we need to do research and train on production data, and so historically we've just been pulling from production and then working with the data elsewhere, if we want to be building things, building tables, building models, making changes, we can't be doing that in production. And another challenge that we then run into is, okay, so if we can get the data into dev and then we have a feature view we want to do, well, in order to get that feature view back onto dev, we're going to have to go through their whole, continuous deployment process, which, as we should, but if we're just iterating and doing research and this isn't necessarily the final version, we can't see everything that we need. So what we've worked out is the idea of having those research institutions part of a research data share that goes from prod to dev. So we'll have a data science development space within our dev instance where we can work with that production data, client data, and do that research, all obfuscated for any PII, et cetera. And there we can iterate and prototype those feature views. And then once we've committed to a feature view, and these are just dynamic tables in Snowflake, just dynamically updated based on whatever schedule we've set. Once we've committed to a feature view, both figuratively in the sense that we, that's the one we want, and literally in that we've committed it to Git, we can copy that, send that into that deployment pipeline that our Illuminate development engineering team, then they'll need to do those reviews and all of that and promote that into prod. At that point, then we can also have the trained model be copied over into production so that now those same feature view definitions that we created in dev and just got automatically deployed into prod are being used on that same trained model that got pushed into prod so that we can push those predictions through. And that way, we can make these data science models, predictions, features available to our internal analytics teams so that they can use those as well, to our product teams who want to surface those in our products, as well as, to clients who, maybe a premium tier of, data science informed model features that they can get from their Snowflake Reader accounts. All right, how do we do that feature engineering? Looking at those views. We use Snowpark for this because it allowed us to quickly iterate and explore our data to build features from the sequential login sessions. And, this is where that lazily evaluated data frame is really useful because, if I've got billions and billions of clicks, I don't need to download them. I need to create that data frame and only process that, at the point where I need to actually, say, review it at a high level, I can aggregate it and look at statistics, but not actually pull down all of that data. And that allows us to iterate and think through things and use, Python syntax that we as data scientists are comfortable working with and familiar with. Under the hood, it's really just creating a SQL query, but this allows us to kind of dynamically build that and then lazily evaluate, save it as a feature view. Yeah, and so for this project specifically, we split out each step in the sequence is the categorical encoding of the page and the number of seconds spent viewing the page. So you can see some different distributions, in our product, like the outline or the stream are kind of the central course landing page. So that's going to have a lot longer and a wider variation of views. But then you can see, somebody clicking over to grade tends to be a short view, just like, hey, what's my grade? Gap is when they leave the course and return. So just looking at, we were able to take all of this data, this very granular level, and transform those using Snowpark. And to that end, we are able to chain those feature views together to allow for simple data refresh downstream. So if you haven't used dynamic tables or the feature view functionality in Snowflake ML, it allows you to specify, of course, how frequently you want them to be refreshed. But if you've got multiple tables in a row and the one at the end needs the most updated data coming down the whole line, you want to be able to specify that and say, I need this updated every day, but don't update it until you've updated all of these, right? So you specify it as downstream, and that allows you to plan that out. So you see at the end, those are kind of the last step of the features that are going into the model. And it's, why do I have 4 other tables beforehand instead of just having all of those transformations in one, which is they're split out based on like windowing and other things to improve query efficiency, or if features more upstream are going to be used for something else as well, other experiments. But that way, if you split it out in a way that improves the query efficiency and don't include multiple window grains within one query, it can incrementally refresh. If you have multiple window grains in one query, you're going to end up refreshing the whole table every time, which nobody wants to pay for. So yeah, that allows you to incrementally refresh. All right, we looked at Snowflake ML before, and it's really changed a lot in the last year or two, and there's been a lot of cool new features that we were excited to dig into. But one of the things that kind of prohibited us from getting into it before was, like I said before, we have a really robust use of Git and data version control, which is an open source package for data science pipelines. I really enjoy using it. It's really helpful for versioning your data the way that you version your code. And then each of those versions of your data are linked to the Git commit that created them. So if anything changes in your code or your data dependencies for that stage, it'll rerun, right? Because something changed, not because, I have to know that I need to rerun this one and that one, right? So it's very simple. And while Snowflake ML has the ability to version your feature views, version your models, we didn't have that granular level, I think, that we were used to working with. So we created an internal tool set that wraps around the Snowflake ML API. And basically, it hashes some little pointer files that are really the definition of the table or the model, so that if anything changes in the table definition, then that can be used in DVC the same way that we always do, but we're not having to download all that data, right? Previously, to run a DVC pipeline, in order to know that something changed, I had to download all that data into the EC2 instance, hash the data. Okay, now I know the data changed. Now it can run the next step. This is a much lighter lift. So it knows, okay, something changed. So when I query Snowflake, it will be different. So now it will run that step. So that's really helped us to accelerate that research and to accelerate adoption on our team within the tool set that our data scientists are used to working with. So model training. We got all that data, we processed it, we've got feature views. And our model for this project, we were using an auto-encoder to take the full unaggregated sequences And in this case, it's a bidirectional LSTM variational autoencoder. And an autoencoder is a neural network that is trained to learn itself. So usually when we train, a predictive model, we're training for some target, yes or no, some continuous variable. In this case, we're saying, learn your own identity. But obviously, that's a pretty easy model. Multiply by 1, great. But that's not what we want. We want it to learn something about itself. So the layers inside of the neural network compress the data down into, a smaller shape and embedding and encoding. And then you're calculating your loss based on the decoded data from that inner encoding. There can be multiple levels, multiple sizes. Obviously, the sample is just very small. And so you do all of the training with end-to-end encoder, decoder, comparing the loss between the decoded output and, the input. And then when you want to go, use it as a dimensionality reduction, just chop off the decoder, feed input in, pull out the encodings in the middle. So this we did with PyTorch on using the PyTorch data connectors that Snowflake ML has. This streams batches directly from your Snowflake tables, which are those features that we had shown there. Streams those batches directly without loading into memory. And in this case, because it is a recurrent neural network, it's more than 2 dimensions, right? So every sample is a sequence and features describing that sequence. So we use vector data types in those features that then when those come through the PyTorch data connectors, they come through as deeper multidimensional PyTorch tensors that can be fed in batches into a PyTorch model. And we used multi-node distributed training with distributed container runtime. Initially, this was only available on Snowflake notebooks. And, I talked a lot about how we have our development processes and our DVC pipelines that we like to use. So going into Snowflake notebooks kind of broke those pipelines, but we were doing it for exploration purposes, for experimenting. And we found it really useful because, experiments that were taking hours to run, locally or on our EC2, we're completing in about 20 minutes when we did them in distributed runtime on the Snowflake notebooks. And what was really great is that then the Snowflake ML team released Snowflake ML jobs. So this new feature, you can launch any Python script or function on Snowpark container services from whatever script, IDE, whatever's orchestrating this whole process. Launch that on Snowpark container services. And that allowed us to take advantage of the distributed compute in our existing research and development framework. So this saved us days of training time and allowed us to expand our hyperparameter search space a lot because it was simple and fast to launch those jobs on the Snowpark container services. Now the ML jobs feature, I believe, is in general preview, and the distributed compute on ML jobs, I don't know where that is. I'm not a Snowflake employee, but it was really useful. And, we built all of our kind of model architecture and our training loops in PyTorch on the Snowflake notebooks. And then once that ML jobs distributed training feature dropped, could move that all right into our pipeline. And so here, now it fits into our usual workflows and how we track our commits and our data versions and our models. Orchestrator, which in this case is being run on EC2, but it's not pulling all the data. It's really just orchestrating the Snowflake work. And it's, using that DVC pipeline, launching an ML job on Snowpark Container Compute, can't talk, which is then distributing that work across however many nodes you specify, and using PyTorch distributed training APIs in order to coordinate all of that training. And ultimately, we take whatever, results and logs we want to get out of that training and move those over to a Snowflake stage so that that orchestrator can then pull them down, put them back into our pipelines, have those results that we need to understand, how that model training went. So what happened? What are some of the results here? So we conducted a hyperparameter search across a couple different dimensions like learning rate, the weight decay, the batch size, and the model depth, experimenting with different sizes for the encodings and different, levels of hidden dimensions on the way down that encoder-decoder framework. And then we had a couple different metrics that we were comparing those encodings on because, of course, evaluating some more unsupervised encoding and embedding can be a little difficult. We didn't want to just rely on one metric. So you can see here we have the best reconstruction loss, the reconstruction loss being how well did it reproduce itself given the constraints of the model. And then the normalized eigenvalue sum, which is really just the explained variance, of the eigenvalues and, all divided by the largest one. So basically, if all of your variance is going to be explained by the first principal component, the result's going to be 1, which you can see in the right-hand lower corner. Those ones didn't go as well. They have a higher reconstruction loss. We want a higher NE sum and a lower reconstruction loss. So you can see a whole chunk of those down there that don't look great, but we were able to see some good results up there in the upper left corner. So we move forward with some of those models in working on our clustering. Now, first, these are just some of those trainings. Forgot I put this here. Some examples. On the top, some of the better results that you saw in that upper left-hand corner. And on the bottom, some worse results, all compared to a bootstrapped baseline loss for the reconstruction. So you can see, how much better some of those did at learning something about that data and reproducing itself. So, our ultimate goal here is to be able to get some interpretable personas about these type of session logins. So we clustered those encodings using a Gaussian mixture model, 30 segments here, and began investigating their interpretability. So this is a heat map of the distances between the cluster means. So you can really see kind of the box around the outside, which is there's a couple, cluster 1 and 4, as well as 26 and 27 are a good bit further away from the rest of the clusters. But use this as a good start for investigating some of those things to see if there was interpretability here that came out of these encodings. And if you look at cluster 4 and cluster 27, you can see they're both further away from everything else, but they're closer to each other. So I said, what are these? And it turns out that basically all of Blackboard's calendar functionality use fell into these two clusters. And you can see, however, that one of them, cluster 27 in orange, one of them has much longer login sessions with a greater number of clicks. And, the other one, cluster 4 in blue, looks like somebody just logged in, checked the calendar, said, oh, yep, I don't have class today. Okay, bye. So it really shows that those clusters and those encodings are learning something real about the data, about those sequences that we've put in. And so another example from that, you can see these are just kind of lines of those, examples of specific sessions, and each color line is a different category and the time that they spent on it. So on the top, you can see cluster 4, the whole session is 8 seconds long. They checked the calendar. They went to the outline, which is sort of the intro landing page of the course. They checked the calendar. They got out of here. But at the bottom, you can see in cluster 27, just like we talked about, much longer login session, spent a lot more time looking at the calendar. Maybe they're thinking about all of their due dates. And, obviously this is just conjecture, but, they're clearly both different from other clusters in that they really are related to the calendar and scheduling, but they're also different from each other in these other ways. So what is next? We're coming up on the end here. What is next is, I talked about some of that, future state architecture that we are currently working towards. We're doing a lot of research and exploration on this project, but to really unlock and accelerate this work on future projects with what we've learned from this, we need to expand our data set that we have access to within the dev instance that's coming from the prod client data. So that is, creating that research share from prod into dev to give us, we're calling it our data science lab environment. And that's, where we can build things in our own iterative, rapid prototyping way without having to, worry about pushing into prod until, we're ready to. And so we want to optimize access to that. We're working with our engineering and architecture team to set all of that up. And then we want to, on the project itself, move forward with researching and validating, like, what of these types of behaviors and combinations of types of behaviors are predictive of student success. Because like I said before, this is all part of our student engagement, their engagement in their courses, our initiative around that. And so we have models that look at how engaged students are in their courses, and, how does that relate to whether they pass or fail those courses. And then, how does this work and these clusters tie to that? And we're also looking at these as a descriptive, feature that we can push into products as well to let instructors know the kind of engagement that students have with their courses. And then, the other end of that, future state deployment, we need those pipelines for deploying those feature views and trained models onto our production Snowflake so that, the research that we're doing on our legally approved research institutions, the results of that research can be applied and benefit all of our clients across our products on their data. So I think that's it. Thank you.